So yeah, hi everybody. We are Cornell Hyperloop again. So this is going to be our levitation system design. If you want to go to the next slide. Yeah, I guess you probably heard the team introduction in our previous presentation, but just to reiterate, we are Cornell Hyperloop. We were established in 2017, and this year, 2022, marks the beginning of our 2-year design cycle, and it's our first time tackling magnetic levitation propulsion. So we are in the initial phases of our design.
Alrighty, so this is an overview of our levitation system, and honestly, sort of the all of our magnetic systems as a whole on the pod. The way we wanted to approach designing the system was more holistically and ground up. So the first thing that we wanted to set about doing was defining our engineering requirements, because those are really going to be because this is kind of a specific and quite a difficult problem to design around. We thought that very clearly defining what we could work with and the space we had and what kind of materials we could use was very important. And the most driving, the highest level requirements that we found were the CHC track and the pod specifications. So these are things like the dimensions of the track, what the material was, and the also very importantly the no entry zones. So the on our pod we've arrived at this configuration here of using a linear induction motor for our propulsion, and then a system of electromagnets at the front and the back of our pod, and in order to provide a much larger, more dominating levitation force. And also because of the CH specifications, we know that these magnets can lift a maximum weight of like 256 kilograms. So we use this mass as the requirement mass that we know that the electromagnets need to actually lift. So what are the drivers of a successful levitation system? So from our research, we know that successful levitation utilizes two phenomena. One is the Lorentz force law, and the second is the successful generation of eddy currents. So this graphic here on the left is a graphic displaying how you would go about calculating a levitation force using an image coil system. So without getting too into the woods about with this diagram, this is essentially an electromagnet, a coil electromagnet that you run a controlled current through, which is what we would be controlling, levitated at a certain height. And what happens is the eddy currents are generated as a result of a changing magnetic field. And there's a few different ways that we could go about calculating this. On the right, there are a few different equations that are listed in the references at the end of this presentation. But these eddy currents are really what are a lot of the main thing that we rely on in our levitation system. So how do we actually generate eddy currents? So we need two things in order to generate an eddy current. One is a changing magnetic field. This can come in the form of relative motion, or in the change of an actually alternating magnetic field. So that's the first thing. And the second thing we need is an actual conducting plate in order to induce those eddy currents into. And this is most graciously provided by CHC in the form of our aluminum track. Because our pod is moving in relation to the track, of course, we have naturally a changing magnetic field just as a result of relative motion between the two. But if we were to not be moving, then this is a different design consideration that we need to take into account. So in order to actually go about designing our system, we wanted to define the states of the pod very clearly. And the highest level that, again, we found was the pod could have two states, not moving or moving. So in the state 2, which is what we've defined as the pod having a non-zero velocity, again, the changing magnetic field that we need to induce an eddy current and thus induce a lift force comes as a result of relative motion. So we can actually get this just by using electromagnets if we would like to control the actual magnitude of the lift forces as a result of a controlled current, or we actually can just use a regular permanent magnet such as a neodymium as a common one. This would lead to just a constant lift force and only changes based on speed. But if you wanted to use a DC electromagnetic system, then you could actually control the lift force a little bit more. But in state 2, because we don't actually have a relative motion between the two, a permanent magnet and a DC electromagnet will not work. As a result, we would need to use an AC electromagnet in order to just flip the polarity of the current and therefore the magnetic field in order to generate this lift force that we'd like when we're actually stationary. So given these two states, we sort of arrived at these two sort of general design configurations. Would we like to use AC electromagnets and levitate when we're standing still, or would we like to use a DC electromagnet and levitate more strongly when we're actually moving? So this was the main design trade study that we had to do because we had to really focus on where we wanted to actually levitate. We would like to we definitely need to levitate while we're moving because the lift force generated by the linear induction motor isn't very strong, and also we need a more dominating levitation force in order to ease with our control systems, which Mihika is going to go into a little bit later. But these two design options are the two options that we think give us the most freedom or the most breadth as far as where we can levitate, like which region we can levitate in. So our first option that we looked into was actually just using a combination of DC and AC electromagnets. And the way that this would actually operate in principle would be when we're not moving, when our velocity is 0, we would power on or supply power to our AC electromagnets in order to create this polarity or this periodic magnetic field, and this would allow us to levitate before the linear induction motor kicks in. We actually start moving, and then once the pod has a non-zero velocity, then we switch our power to the DC electromagnets, and from there we now have a more easily controllable magnet lift force. And then vice versa, when we actually go to slow down, we decrease the power to the DC electromagnets and then switch power to our AC electromagnets. For our second design option, we could look at using just AC electromagnets. This would provide a lift force for both of the pod states. We would be able to provide a dominating lift force when we're not moving, and then also when we are moving. However, this does cause some problems with control, where what frequency do we switch the magnetic fields at, or which frequency do we switch the current at, and then it can lead to an oscillating effect on the pod, which would be quite undesirable. So how does this trade study hold up? The DC and AC combo gives us a nice trade-off of stability and control. The stability coming from we can use DC electromagnets and effectively have a permanent magnet that we can sort of control the strength of when we're moving, which is really nice. And then the control is quite simpler for DC, and then at AC, when we're standing still, we don't really have to worry about our motion. And this is a problem that we've seen somewhat solved in a few areas. So those are two of the main things. But Mihika can go into a little bit more detail about the rest, and then as well as the dynamics and the control of the system.
Yeah, so like Jack said, we have two design options here. So yeah, we have listed DC and AC as higher instability because making the trade-off from AC electromagnets to induce levitation to DC magnets that will maintain levitation with a pod velocity that's not equal to 0 means that we don't experience an oscillatory lift force that we would experience with an AC electromagnet combined with a moving pod. But obviously that creates for a control system that's a little bit more difficult. Another concern that we have with using AC only electromagnets is the thermal strain that we would be placing on our solenoids, since we would theoretically like have to vary the frequency and the magnitude of the voltage to accommodate. But the good thing about the AC magnets is that we reduce the number of components since we don't have two separate systems. But overall, our final decision for our plan of record was to go with the DC-AC combo electromagnets because they work for all levitation regions. And yeah, so that's kind of our reasoning there. Okay, so yeah, to the point of developing our developing a model for the system dynamics and the control, you can see two generalized equations of motion, I guess, for the AC current state and the DC current state. So this aids us in developing the plant transfer function in our next slide, if you go there. Yeah, so linearizing our system using those previous equations help us determine the plant transfer function, which is basically how our system responds to a certain like input like signal or input disturbance. So once we've categorized our plant transfer function, we can use our generalized control system feedback loop to develop our controller function. So going to the next slide. So as of now, our controller is undefined because we have a prioritization on characterizing system dynamics, which means that even though we have our generalized like equations of motion, summation of forces, we actually do need to see how like our specific system is going to be designed and the specific dimensions and everything to be able to characterize exactly how the system responds to input signals. But the anticipated control design choices are that we will be using some sort of lead lag compensator because we are anticipating some sort of time delay from the sensor. And we will also have to consider our rising time and settling time to prevent introducing instability into our system, optimizing steady state error and disturbance rejection. As for sensor choice, which is what informs our feedback loop, we are planning on using IR sensors because they are cost and time delay optimized when choosing between ultrasonic, IR, and LiDAR sensors. And yeah, these are our references. And yeah, does anybody have any questions?
Yeah, we are open for questions now. Anyone having any questions, please go ahead. If anyone else doesn't have a question, I have a small question. Whether your AC and DC systems will be physically different or the same physical setup will be supplied in AC and DC current and then made to work accordingly.
Yeah, that is a big design consideration that we have is can we use essentially like the same one electromagnet on each and just supply a different current. We looked into a few different manufacturers of electromagnets. We, however, couldn't from our research we couldn't find electromagnets that we could just buy off the shelf that would work with both AC and DC current. So if we would like to move with that option, which I think would be a very size, weight, and power efficient way of going about it, we would likely have to manufacture those magnets ourselves, or at least assemble all the components of them ourselves, which would be a lovely challenge to go about taking on. But I think what a lot of our ideology so far this semester has been that we would like to design the system first and then optimize second. So one of the more attractive options right now is to have essentially, I guess, 4 magnets, 1 DCs, 2 DC systems, and then 2 DC electromagnets, and then 2 AC electromagnets, and then just kind of switch which one we actually supply power to. But definitely in the future, I think sort of this using just 2 magnets and just changing what kind of current we apply to it is definitely the design direction I think we'd like to go in.